So I would like to thank the organizers for inviting me and for inviting me to talk. And for inviting me to talk about the Trans-Planckian Censorship Conjecture, which is a very controversial topic. So I will try to be very controversial, this is a warning. However, I will start with something which I would like to be absolutely non-controversial, which is the first part of the talk. So, the introduction. And in introduction, I want to try to persuade you that we do not need inflation to explain the current data. That there are alternatives, and in fact that the criteria for successful early universe cosmology were laid out long before inflation. So that's the non-controversial part of the talk. Okay, so first of all, the data. We see a beautiful monopole of the cosmic microwave background. So this is the projection of the cosmic microwave background sky onto a plane. And you see different colors mean different temperatures, and you see the beauty is that to very good accuracy the temperature is isotropic. Now if we look with much greater precision, then we see some small amplitude anisotropies popping up. And these small amplitude anisotropies we can quantify. So what this shows is angular scale and amplitude of anisotropies. And you see the data, which has the cosmic variance and the statistical uncertainties. And it has a theory curve painted on. And the point that I want to make is that this theory curve was developed 10 years before inflation. So, now, none of this data can be explained in the context of standard Big Bang cosmology. We need something beyond standard Big Bang cosmology. And so what the picture that I want you to carry with is that we need an early universe phase. So if you draw a timeline, and since there is this whiteboard here, so time, space, there has to be some kind of new phase. And a phase transition to the stage where standard Big Bang cosmology applies. And I want to talk about the criteria for the new phase. Okay. So, this you already saw. This is the mystery within standard Big Bang cosmology of why the microwave background is so isotropic. This is a mystery of why it is so spatially flat. And here is a mystery that concerns the anisotropies. So, this is co-moving length scale, so where the lengths expand as space expands. And this is a standard Big Bang horizon. And this is a length scale of stuff that we observe, and the length scale is larger than the horizon at the time of equal matter and radiation, when the seeds for the structures have to have been in place. And so therefore in standard Big Bang cosmology there is no explanation for any of this beautiful data. And therefore we need to go back and we need to have some kind of new phase. Okay, so just to set notation, this is our background space-time. Time, the co-moving coordinates, this is the radius of space, and the expansion rate. Okay, and the two people, or members of two collaborations which worked out the criteria for successful early universe cosmology are Peebles and Yu, and Zunyaev and Zeldovich. And this diagram is from the Zunyaev-Zeldovich paper of 1970. So, time, space, co-moving coordinates, and this is what they call the Jeans length. I will call it the Hubble radius, the inverse expansion rate. And this is the time of recombination. Okay, so what these authors pointed out is that if there are inhomogeneities on scales which at times before recombination looked like they were larger than the horizon in standard Big Bang cosmology, if there were these fluctuations which with a roughly scaling invariant spectrum then these fluctuations will start to oscillate once they cross the horizon, and different wavelengths will oscillate different amount of time. We will catch these waves at different phases, and therefore you will get the acoustic oscillations in the CMB angular power spectrum. So you will get this. In fact, the diagram which I showed you from this 1970 paper has a second part. And this second part shows you the amplitude of the matter perturbations as a function of wave number. And again, you have these oscillations. These are called BAO. So BAO and the angular power spectrum of microwave background were understood 10 years before inflation. So, the question which was not addressed back in 1970 is how does one obtain this spectrum of standing wave perturbations on super Hubble scales? And indeed, inflation is the first theory that gives you a generation mechanism for such perturbations, but it is not the only one. So what are the criteria for a successful new phase? So first of all, the horizon has to be much, much larger than the Hubble radius today. That's in order to produce the isotropy of the microwave background. Then, in order to have a causal mechanism to generate the fluctuations, the scales on which we see today have to be inside the Hubble radius in the early stage, because we can't move around matter on scales smaller than the Hubble scale. So that's the second criterion. The third criterion is only necessary if you have quantum vacuum initial conditions, which maybe the initial conditions are not quantum vacuum initial conditions. So you need to have evolution of wavelengths which we observe today on super Hubble scales. That's in order to get the squeezing and the classicalization. Okay. And finally, the fluctuations have to have a roughly scaling band spectrum. Okay, so these are the criteria. I guess I was going ahead of myself in what I was speaking. That's because I wasn't looking at the transparency. So let me go back. So here is the difference between the horizon and the Hubble radius. The horizon is a forward light cone of some initial Cauchy surface. That carries causality information. The Hubble radius, that's relevant for the dynamics of the fluctuations. That's something local in time. It's the inverse expansion. Okay, and these are the criteria. The horizon has to be much bigger than the Hubble radius. Fluctuations which we observe have to originate inside the Hubble radius, squeezing, and scale invariance. Okay. So, inflation is one way to get these conditions. So in inflation, this is time, this is space, you have this period of exponential expansion. During the period of exponential expansion, as Chris mentioned, the horizon expands exponentially, the Hubble radius remains constant. Scales which we observe today started out inside the Hubble radius, provided inflation lasted long enough. So inflation is a nice solution. There's a time translation symmetry which is responsible for getting scale invariant fluctuations. Now this is one alternative. The alternative is a bouncing cosmology. So here you imagine that there is a contracting phase, some new physics that gives you the transition to standard Big Bang expansion. And so the scale factor contracts, new physics, it expands. Okay, this is time and space. This is the Hubble radius in the contracting phase. The Hubble radius is contracting. And here I draw co-moving coordinates. So fluctuations have constant co-moving scale. So time runs from minus infinity to plus infinity. The horizon is infinite, much smaller than the Hubble radius. Fluctuations emerge sub-Hubble, so it's possible to have a generation mechanism. Okay. Now a third scenario is what I call an emergent universe, where you have some new physics phase, maybe not even a well-defined space, and then a phase transition to standard Big Bang expansion. So scale factor as a function of time. There's what I draw as quasi-static phase, followed by standard Big Bang expansion. Okay? This is a corresponding space-time diagram. So space and time. This is the Hubble radius, which is infinite if the early phase is really static. And fluctuations have constant physical length in this static phase. And so you see, again, you have the horizon, much, much bigger than the Hubble radius. Fluctuations start sub-Hubble, and they evolve on super-Hubble scales. So there are different scenarios in which you can realize the criteria which are required to explain the observations. Inflation is only one of them. Okay, so this was what I want to be the non-controversial part of the talk. So now comes this phase transition in my talk to what I want you to view as controversial. Okay, so, good. Okay. Fine. Now, this, I'm not familiar with Windows, so what should I do here? Press OK.
Behind Windows.
Aha. This is the problem. This is the problem. I have a number of figures now. So I am prepared to switch. However, I'm also prepared to draw the figures on the whiteboard. So is it okay if I use this? Can you all see the whiteboard?
We can move it.
Let's move it.
Okay.
It even has wheels.
Okay. So what is missing here is the switch of a black hole.
I'll even give you a second one.
Okay. So,
Robert, you cannot use your laptop?
I can, but it will cost some time.
Probably less than drawing figures.
I might as well continue.
Maybe while you're drawing this figure, someone else can switch the
Okay,
laptop.
fine. Okay, so black hole has a singularity, a curvature singularity at the origin, r equals 0. However, if the black hole has a charge which is smaller than the mass, then this bad feature, the bad feature from the point of view of classical dynamics and from the point of view of well-controlled curvature, is hidden by a horizon. And so therefore the observer who's sitting outside the black hole cannot see the bad things that happen here. So light only approaches from the outside. So this is what happens for a black hole with charge smaller than a mass. However, if you take a black hole with charge greater than a mass, and such black hole solutions are perfectly admissible in general relativity, then you have this singularity at r equals 0, and the poor observer at infinity, or outside, is not hidden. This is a naked singularity, and information can travel from this singularity to the observer. So, the observer sees a singularity, and the dynamics is acausal, non-unitary. Okay, so the effective field theory, which is general relativity, admits such bad solutions. Solutions in which the observer sees singular stuff and non-unitary stuff. Penrose, in 1968, says that, well, even though these solutions, bad solutions, are solutions of effective field theory, the full ultraviolet theory does not admit such solutions.
So I have a comment. Depends what you call the solution. The solution is simply something that solves the differential equations, or is something that it's the result of reasonable initial data propagated by the
It is
equations.
something that solves the differential
Because
equation.
these two kinds of things
They are
are
very different things. Very different things, and this is tied to here. Okay. So now I can turn to. so this is what I drew. This is what I drew. Now can I still use, now I have to,
So the clicker won't work.
good. Okay, so time-like singularities are hidden by horizons. The singularity and the non-unitarity is hidden from the external observer. Okay. So now, let's look at an expanding universe. And in an expanding universe, there's a unitarity problem. So if you view, as we do in inflation, if we do a theory, quantum theory of fluctuations, then we are quantizing harmonic oscillators. Each co-moving wavelength corresponds to a harmonic oscillator. So the Hilbert space that we deal with is a product Hilbert space over co-moving wave numbers of the Hilbert space of one harmonic oscillator. Now this is an infinite dimensional Hilbert space. In an effective field theory we have to cut it off. And we need an ultraviolet cutoff. But the ultraviolet cutoff has to be an ultraviolet cutoff in physical coordinates, not in co-moving coordinates. Which means that the ultraviolet cutoff is time dependent, and you need to insert more and more modes the further time runs. So this is blatantly non-unitary. Okay. So this is, we already saw it. So now what I want to do, let me continue to the, see I'm being controversial, so I'm soliciting, I'm provoking people. But let me continue the argument and then come back to you. So I now want to translate the Penrose's cosmic censorship hypothesis to cosmology. So singularity means regions of wavelengths with wave numbers greater than the Planck length. The black hole horizon becomes the Hubble horizon. And I want to postulate, and the postulate is actually a postulate that was made by Bedroya and Waffa, that the external observer is shielded from the non-unitarity associated with the Trans-Planckian regime. So, okay. Concretely, this means is that if you have some initial time, t sub I, then at all subsequent times, t sub r, the expansion of the Planck length cannot have gotten you to something larger than the Hubble radius. No initial sub-Planckian scales become larger than the Hubble radius. So this is a mathematical postulate of this Trans-Planckian cosmic censorship conjecture. So now I come back to you.
Okay. My concern is that the way this thing is framed is clearly violating Lorentz invariance, because we are going to cut up wavelengths in a particular frame. This is different from what is done in ordinary quantum field theory, even in flat spacetime. In flat spacetime, we have, in principle, all possible wavelengths contributing to radiative processes, and the cutoff is on the magnitude of q squared. Q is the momentum exchange, and that is a Lorentz invariant quantity. Here we're cutting off, or considering putting an ultraviolet cutoff tied to a particular frame of reference, and that, we have shown it in the paper, leads to very, very serious problems, because the particular frame, information about the particular frame percolates to low energies and generates variations of Lorentz invariance at low energies, so large that we would have already seen them.
Right, so I disagree with the final statement that you made, but not the other things. So obviously, I do not think we can maintain Lorentz invariance on Planck scales. So I am using this picture, which is on the board here, which is definitely not consistent with global Lorentz invariance. Okay. Great, so, and this may be wrong, I admit, but let me continue.
Okay.
Well, to the consequences. So what are the consequences of this conjecture for cosmology? Okay, so first of all, the justification. I think I've spoken enough about the justification. but I'll let you see it again. The one thing I want to mention is why in cosmology do we focus on the Hubble scale as a thing that generalizes the black hole horizon? And the reason is that on length scales smaller than the Hubble radius, fluctuations simply oscillate. They don't grow in amplitude. Whereas on scales larger than the Hubble radius, fluctuations grow in amplitude and they might classicalize. And so the reason that we are using the Hubble horizon is that essentially we don't want things that classicalize to be sensitive to the Trans-Planckian region. So this is the region for focusing on the Hubble radius as a key scale. Good. So now, if you buy this conjecture, what does this imply for the various early universe scenarios? So first of all, for standard Big Bang cosmology, there are no implications, because in standard Big Bang cosmology, no fluctuations ever exit the Hubble radius. This is illustrated here. Time, space, this is this Trans-Planckian region, this is the Hubble radius, scales only enter. Bouncing cosmology. As long as the energy scale at the bounce is smaller than the Planck scale, then no scales that ever cross the Hubble radius were Trans-Planckian, as this diagram clearly shows. So bounce scenarios, including the ekpyrotic scenario, are completely consistent with the TCC. Now what about an emergent scenario, where there's some unknown structure space-time, maybe not emergent space, then a phase transition to standard Big Bang expansion? Again, the length scales of stuff that we see today, the length scale of anything that has ever exited the Hubble radius, is larger than the Planck length. So we are shielded from this region. There are no constraints on emergent cosmology from the TCC. But in inflation, it is not the case. It is exactly this exponential expansion of space which renders the external observer sensitive to this Trans-Planckian stuff. So this is what we called in 2001 the Trans-Planckian problem, but now it's been elevated to a principle. Good. So now, if we want to stick to inflation, and we want to be consistent with the Trans-Planckian cosmic censorship, and if we want to keep inflation as a possible source of all structures that we observe today, then this space-time diagram has to be saturated. So this is time, this is space, physical distance. This is a period of inflation, and this is a Planck length. And we don't want inflation to last too long, because we don't want the initial Planck length to become larger than the Hubble radius at the end of inflation. On the other hand, our current Hubble radius has to originate inside the initial Hubble radius, otherwise we have no causal mechanism of structure formation. So, demanding that this curve originates inside the Hubble radius says that inflation has to last sufficiently long. The TCC says that inflation cannot last long enough. Now the two are not a priori in conflict, but they require, so this is a TCC, this is a condition that our current Hubble radius starts out sub-Hubble at the beginning. They are consistent provided that the energy scale of inflation is sufficiently low. 3 times 10 to the 9 GeV, not 10 to the 16 GeV. And since it is this energy scale which sets the amplitude of gravitational waves, you find that the amplitude of gravitational waves divided by the amplitude of cosmological perturbations has to be smaller than 10 to the minus 30. So in inflationary models, which are consistent with the TCC, you get this prediction for the tensor to scalar ratio. Okay. So now if you want to have inflation as a source of the density perturbations, and you want slow roll inflation, then the slow roll parameter has to be extremely small, which means that the scalar field rolls an extremely short distance, which means that you need extreme initial condition fine-tuning, such that you land on the slow roll trajectory. Okay, so inflation is not completely ruled out, but extremely constrained, compared to the other scenarios which are not constrained by the PCC. Okay, so how much time do we still have?
About another, well, we're going to have, we have another half an hour plus,
Okay, so-
for including
and I want to-
discussion, so another 15 minutes, 20
Good.
minutes.
So now there's a completely separate attack against inflation, and this comes from the effective field theory point of view. So these are the swampland criteria which Chris alluded to. So inflation is formulated as an effective field theory. So it is effective field theory based on general relativity, and matter treated as an effective field. So now the conditions to get inflation using this description are the following. So I use a canonically normalized scalar field to get inflation. This is the equation of motion. If I want inflation, I need the potential energy to dominate over the kinetic energy, and that means that the slope of the potential has to be small. And inflation has to last a long time, and that means that the second derivative of the potential has to be very small as well. So these are the conditions to get inflation under the effective field theory assumptions. And if we want the inflationary trajectory to be a local attractor, then we need large field inflation. Okay, so these are the conditions on an effective field theory description of inflation. So the question is, can we actually realize such an effective field theory from the point of view of quantum gravity? And I will now assume that it is string theory which gives you quantum gravity. So, does inflation actually arise from superstring theory? Okay, so now let me step back and make another couple of controversial comments. So, in field theory, in effective field theory, we have a huge landscape of possible solutions. Field theories exist in any dimension of space-time. You can have any number of scalar fields, any potentials, absolutely unconstrained. In field theory, you can get anything you want. In string theory, not. String theory is extremely constraining. The number of space-time dimensions is fixed. Scalar fields are moduli of this string theory. Everything is very constrained. You see, it's not what you normally hear. So, only a small set of effective field theories are actually consistent with string theory. The rest lie in the swampland. And this is a famous picture, not drawn by myself, drawn by someone else. So there's this underlying quantum gravity theory, which picks out a small subset of possible effective field theories. And we now want to see whether inflation fits into this small subset. The answer will be no.
Sorry, the landscape is picked up by your conditions for inflation or by the theory?
No, the landscape is the subset of effective field theories which are consistent with the underlying quantum gravity. Okay, so now the conjectures which were made based on superstring theory on the subset of consistent effective field theories are the following. First of all, the effective field theory is only valid if the field range is smaller than n Planck times a constant of order 1. If the field dominates the evolution of the universe, then the potential of this field is constrained this way. So the slope of the potential has to be sufficiently large, and the second derivative has to be sufficiently large. Okay, so let's go back to inflation. Maybe let me say some reason for that. So phi, a scalar field in string theory is some modulus field, and if in string theory the modulus changes by a large amount being n Planck, then you reach a situation where a new set of states of string theory become massless, in which case you have to change the effective field theory. So that's the reason for this field range condition. Now, The origin of the de Sitter conjecture, so the steepness conjecture on the slope of the potential, comes from the fact that in string theory these moduli fields are stabilized by stringy effects. And the stringy effects give you a particular potential. And it turns out that the potential is fairly steep. And you can see that an example worked out in this paper. Okay, so these are the conditions on an effective field theory, which is consistent with string theory, field range, and slope condition. And this is what inflation requires. And you see that the conditions are exactly opposite. So therefore, slow roll inflation is in the swampland. False vacuum inflation is also in the swampland. Now, warm inflation can actually escape from the swampland.
Robert, can you just go back? Do you have the inequality the right way on your conditions for the second derivative? Go back one more. Or
So this is for inflation.
No, but go back to the conditions. Is that, do you mean less than in the bottom one there?
This means sufficiently negative.
Oh, sorry, I
It's
missed the
very
negative. Sorry,
tachyonic.
yeah. Sorry, I missed the negative sign. Thanks.
Okay. Good. You see, I'm now getting close to the end. So, inflation does not naturally emerge from superstring theory. And that comes from the swampland criteria. And based on the TCC, it looks like inflation is highly fine-tuned. But now, we do not actually need inflation. So what about alternatives to inflation? Well, one alternative to inflation, which I'd like to remind you of, or maybe tell you of for the first time, is the ekpyrotic scenario. This is a particular contracting universe which is driven by a scalar field with an equation of state where the pressure is much larger than the energy density. This is obtained by having a negative exponential potential. And such negative exponential potentials arise completely naturally from superstring theory. So, now, unfortunately there are a couple of equations. This is a negative exponential potential. This gives rise to a power law contraction of space. So time goes from minus infinity to 0. But P is very small, which means W is very large. And this is how the field evolves. So negative exponential potential, this is the field. Okay, so now if you look at one Hubble expansion time, you find that field moves only a slight distance. You take the potential, you calculate the derivative is large. You look at the second derivative, it is large. So this alternative to inflation seems to be rather consistent with not only the TCC, but also with the swampland criteria. Good. The one challenge for the ekpyrotic scenario is to get the scale-invariant spectrum of curvature perturbations. And I want to advertise this paper, where we've been able to achieve that by adding a unique stringy ingredient to this ekpyrotic scenario. Now, in an emergent scenario, you're also safe from the TCC, as I showed you before. And if the emergent scenario comes from string theory, like it does in string gas cosmology, then obviously you are basing it on string theory. So it is not in the swampland. So, my final word is, alternatives to inflation appear to be more promising in light of fundamental physics. And when I say fundamental physics, I hesitated a little bit because I'm now saying, actually I should have said in light of string theory. Thanks.
Cosmic censorship hypothesis. And so there are a few things where I'm getting skeptical. One is, you talk about censoring failures of unitarity. I would have thought that string theory was a unitary theory. So
Yes.
Why do we expect there to be failures of unitarity coming from Trans-Planckian physics?
Right, so see, that's a very good question. So, if string theory is indeed correct, then we've solved the unitarity problem, and we don't have to worry about TCC. But then you see, you are to show that inflation arises from string theory. So you sort of have one criticism of inflation which is general, which comes from an analogy with black holes, time-like singularities being hidden, and the other one comes from string theory.
I think I have a finger over here.
So you explained to us that the CCC implies that we cannot test wavelengths in the CMB that were sub-Planckian at some time in the past. What about wavelengths that we test in this room, which are way smaller than the ones in the CMB, and therefore they could be coming from Trans-Planckian physics?
Now the TCC says that not only modes that we measure in the microwave background could not have come from the Trans-Planckian region, but nothing that classicalizes could have come from the Trans-Planckian region. So that includes everything that we measure today.
But we measure today very, very short wavelengths in the lab, like in particle physics detector, and they become Trans-Planckian much before the inflationary epoch, if you propagate them backwards in time.
Okay, so, but you have a mixing, you're in a highly nonlinear regime.
What?
So things that we measure, we are measuring things in a local system, which is decoupled from the Hubble flow.
Right, but it seems to me that the problem is still there. They were transplanted in the past and they are here, so.
Okay, let me. So maybe the answer is that you have to move this surface sufficiently far into the future to avoid this problem.
And cannot you do the same with inflation? Just put that surface whenever the mode that we see today become super-Planckian, out of the Planckian.
Right. Okay. So there is an approach to studying fluctuations in inflation where you have a new physics hypersurface where you say fluctuations are generated whenever the wavelength is equal to the Planck length. But that means that you have a time-dependent Hilbert space. So we are saying we don't want to do that in cosmology, and then that's why we postulate the TCC.
Okay, Rich.
Yeah, this is also related to Jim's question. If it seems that if you come to the conclusion that inflation is not compatible with string theory, then this doesn't work and you wouldn't need the TCC, which means that, as I would understand it, the TCC becomes really important if you're willing to assume that string theory does not work and no other unitary theory at Planck scale works either. So my question, I mean, we have talked about this a little bit more already, but my question is this the focus of your argument, a situation where we don't have a unitary theory, there is no unitary theory at the Planck scale at all?
So I think I agree with everything you said, except for the last point. So yes, if string theory is correct, if that gives the correct description of all length scales, in that case, if you could get inflation from string theory, we would have no reason to worry about the TCC. But the problem is that we don't seem to be able to do that. But I don't necessarily, I would like to have a unitary theory. But that's maybe my prejudice.
Alexei?
Okay, so indeed, in fact, repeating the question, and let me remind you that it was the same year at which Robert published his paper about Trans-Planckian problem. I made a reply, in some sense, as the title of the paper was something like, Trans-Planckian problem for inflation. First, as you all already mentioned, if all inflationary models assume that Planck's invariance is not broken at the characteristic energy of inflation, which is at least 5 times less than the Planck energy. Of course, it's an assumption, but okay, why not? And second, and this is in fact refers, I think it would be a kind of philosophical question, but I think a useful method for any proposed new theory to check it not before trying to use it in case of inflation. Let's consider a representative universe which also expands with acceleration, and once more, without any assumption, any theoretical assumption about Lorentz invariance, let me remind you that the theory of generation of fluctuations is a particular case of a previously developed theory of particle creation in cosmology. Okay, we indeed have flow of Trans-Planckian modes far over Planck border even at the present moment, but we don't see any effects. And in fact, it can be easily proved that from absence of the excess of high energy particles, from the fact that the grain, that's a Kuzmin bound is actually confirms, it follows that there can be no Trans-Planckian effect independent of the present value of the Hubble expansion, and there even can be no effect proportional to h squared. What is possible, what is not excluded, effects proportional to h4, but h4 effects are predicted by the standard theory of particle creation in cosmology. So once more, if we assume that accelerated inflation in the course of inflation is similar to the present accelerated expansion, then okay, the statement is no Trans-Planckian problem. And then finally, just using the same general method regarding the Planck conjecture, I would say that indeed we are eager to for some definite prediction from string theories, because we expect them that they not make only conjecture, but they give us actual, at least some target values for twist coefficients C1 and C2. From the observations of the present dark energy, it's already known that if you try to use the same argument for the present dark energy, it follows that the coefficient C1 should be less than 1/2, and coefficient C2 should be less than 1/10. But what astronomers need are not only conjectures, but it needs at least some target value. So I would like what I am eagerly waiting from specialists for some definite predictions, at least for some specific models, which can be checked by observations. Some definite
let me
predictions about the coefficients C1 and C2.
okay. So let me actually give you some specific predictions for observables, which come from a string theory emergent model, just to show that we can make predictions. So now we have 4 observables that we aim for in early universe cosmology. We have the amplitude and the tilts of the spectrum of cosmological perturbations and gravitational waves. Okay, and a prediction will be a relationship between these 4 quantities. And so, just to give you a particular prediction that came from the string gas scenario, is the tilt of the spectrum of gravitational waves is equal to 1 minus n sub s, which is a tilt of the scalar modes, whereas typical inflation has a different consistency relation. And R, which is the amplitude of gravitational waves divided by the amplitude of scalar perturbations, that will be of the order 1 minus ns squared. Okay, so in the context of this model, this is a toy model based on ideas of string theory. I want to emphasize toy model, it's not generic. In this toy model, we have a mechanism that stabilizes all extra dimensions, and that therefore we can calculate these order 1 coefficients. And the order 1 coefficients, they turn out to be something like 1 over the square root of the number of extra dimensions. And I might have forgotten the exact value, but you can look, you can see them in these in the paper that I referred to. So we are actually working towards the goal. We are not general, but again, this was in the context of a particular string-inspired model, but we are working towards the goal of making actual predictions and quantifying these order 1 coefficients in the small black criteria.
Chris?
Thank you. So I have a question in a similar direction. Really, maybe you said that, but then in that case I missed it, I'm sorry. So what's the degree to which alternative theories, such as the epirotic scenarios or maybe generic bound scenarios or emergent universe scenarios, actually get you to something like the correct angular power spectrum of the anisotropies? Is that comparable to what you get sort of generically from inflationary models?
See, this is what I started out with, what I wanted to be the non-controversial part. So, what I was saying that in all models which satisfy these criteria, which I had at the beginning, these 4 criteria, namely horizon much bigger than the Hubble radius, fluctuations emergent in sub-Hubble, a roughly scale invariant spectrum, which all of these alternatives give you, then you get the angular power spectrum of the microwave background. You get that right, because they are the 6 parameters which you are fitting are the 6 parameters in the late-time cosmology.
And sorry, and these alternative models, they can satisfy these 4 conditions?
Yes. However, from the point of view of effective field theory, inflation is the only one which is self-consistent. In all of these alternatives, you have to add things which, from the point of view of effective field theory, are not self-consistent. So, for example, in a bouncing scenario, you have to add a bounce. New physics, which gives you the bounce. Now, I think I can give you plausible ways to do that, but they are not well controlled as an effective field theory. But you see, self-consistent doesn't mean consistent. So I think the problem for the alternatives is that they are not self-consistent as effective field theories. And I think this affects all of the alternatives.
Daniel?
Okay, I have one comment and two questions. Sorry. The first comment is, we have a rigorous result showing that if you remove from the theory modes in a Lorentz violating invariant Lorentz invariant violating way, you generate definitely large violations of Lorentz invariance at levels would have been observed long ago. This is a result in a paper 2004, Fist of Letters, so forth and so forth. It was developed at the time in which looking for effects of quantum gravity phenomenology was in vogue, and people were looking at modification of dispersion relations. We encountered this result that if you remove from the theory modes, all appearances of the modes, that means either real or virtual modes, in this way you generate things that are ruled out by observation. So my question is, my first question is, do you want to preclude the existence of those modes, of those ultraviolet modes, or you are only precluding their classical excitation, because those two things are very, very different. And the second question is regarding the bounce models. If the theory is time symmetric, time inversion symmetric, and our current state of the universe is in some sense unlikely given what we think to be a natural early state of the universe, wouldn't the pre-bounce state, the collapsing state, also be very, very unlikely given the need for the bounce state to occur later on?
Okay, so to answer the first question, I don't want to preclude the existence of these modes, just their classicalization. And I completely agree with your criticism of the bounce. I'm not saying that what happens after the bounce is going to be a generic outcome of an initial state. One thing to keep in mind is, though, that one of the bounce models which are presented was sort of the symmetric bounce, but fluctuations break the symmetry. But that's not relevant to your question. So I agree that in a bouncing scenario, in the standard symmetric bouncing scenario, there is a fine-tuning of initial conditions. In the ekpyrotic scenario, you can argue, similarly to what happens in large field inflation, that you have a local attractor. The ekpyrotic scenario, the ekpyrotic phase of contraction, is a local attractor in initial condition space, like large field inflation.
Josh?
Clarifying question. You talked about, at the beginning, we end up building a quantum field theory with the co-moving frames, but then when we want to express the UV cutoff, we have to use quote-unquote physical coordinates. What's the difference conceptually between co-moving frames and physical coordinates?
So the way that I would like to visualize that is we measure distances with rulers. So in an expanding universe, the ruler retains constant physical size, even though space is stretched.
Okay, so what's the problem then using quote-unquote I think I understand, but using non-physical coordinates to express the UV cutoff?
So the problem is that if we have a cutoff, a UV cutoff at constant co-moving coordinates, then if inflation lasts a long time, then on R scales we have no modes, which is a disaster.
That is everyone I have on the list. Is there another question from anyone?
Robert, so this is sort of following up on what Ricard and I were saying, but I think maybe I misunderstood the character of the argument. So initially, so your response was very helpful. Tell me if the following is a reasonable reconstrual of what you said. Is the idea that what the Trans-Planckian censorship conjecture is doing is effectively explaining why inflationary theories would be in the swampland. So inflation seems to allow for these Trans-Planckian modes to get blown up and then be observable classically. If we conjecture that any reasonable unitary sub-Planckian physics is going to satisfy the Trans-Planckian censorship conjecture, then we aren't going to see Trans-Planckian modes get blown up in this way. Therefore, insofar string theory is a reasonable unitary Planck scale physics, we can conclude that string theory can't be the kind of theory that gives rise to inflation.
Actually, I'm not so sure that I agree with that. So, see, so let's assume that string theory really gives you total control of all modes. And then, if you could get inflation from string theory, there'd be no problems. Then you would actually have shown that the TCC is wrong.
Okay, but so that seems fine. I guess the issue is if the TCC is supposed. Do you have a slide where you just state what the TCC is?
So this is the last equation. So the statement is that under cosmological evolution, no scale that was sub-Planckian at the beginning of time t sub I could ever have become super Hubble.
So is this a conjecture about our universe? Is it a conjecture about the dynamical properties of any theory satisfying certain conditions? Is it a conjecture about particular theory?
Okay, now these are different possible versions of the TCC. So the question is, what is the time t sub r until you want, which you want to allow in this equation? So in inflation, you take t sub r to be the end of inflation. And if you build in a post-inflationary phase, then since no new modes ever exit the Hubble radius, it is satisfied. But I fear that I'm not answering your question right.
Well, let's discuss outside of the discussion.
So when they, well, what's TR? So just, I think this is going to your question if I put my own finger on it. So in the ekpyrotic case, what's TR then?
So, see in the ekpyrotic case, then let me. Okay. So it is similar to this diagram. So you pick an initial time and you demand that no length scale, which at the initial time was in this danger zone, ever became larger than the Hubble radius. So in the case of the ekpyrotic scenario, this t sub r is any future time. T sub I is whatever time you choose at the beginning. For example, you go to minus infinity. Whereas for inflation, you choose t sub I to be the beginning of inflation. Or if there's a pre-inflationary phase, then you have to take t sub I to be the beginning of the pre-inflationary phase. And then you get stronger constraints than the ones that I listed.
Okay. Then I think we really are out of time. There's coffee, I believe, and thank you very much, Robert.
Trans-Planckian.